So welcome. This is the 6th edition on the workshop on energy efficient machine learning and cognitive computing. I'm Michael Goldfarb. I'm one of the co-organizers of the workshop, and I'll be chairing the first session this morning. I just want to thank everyone for joining us online today. This is the first time that we've done the workshop virtually. Hopefully it maybe is the last, thanks to COVID, but we're excited to be able to put on, largely a similar program as to what we've done in the past. So we will have speakers and keynotes throughout the day, as well as some paper presentations and a panel discussion later in the afternoon. Our speakers, and for those of you who registered, will be able to participate over Microsoft Teams. And our hope is that members of the audience will contribute questions at the end of the various talks. I would like to ask that everybody double and triple check that they mute themselves while people are speaking, so that we can ensure that disruption is kept at a minimum. And for folks who could not join us on Teams, we have a YouTube live streaming link that we've made available to anyone around the world who would like to join in the workshop. And this is a very exciting time to be building ML systems. And in the last 2 years, we've seen huge growth in deployments and many amazing breakthroughs and capabilities. None of this would have been possible without the rapid advancements in processing efficiency that have been attained in the last couple of years. And I think this is true regardless of whether you're running and training state-of-the-art models at hyperscale on giant clusters, or you're putting a model onto extremely resource-constrained devices like microcontrollers. I think across the spectrum, efficiency really is the key. And to achieve this efficiency, we have sort of 3 pillars, and I think you'll see these 3 pillars throughout the talks today. These pillars are hardware, software, and systems. So the hardware, we have people building custom accelerators, looking at new instruction sets, fancy memories, interconnecting multiple processors, basically building the underlying machinery that enable all of this. And then on top of that hardware, we have software, and that software has to be built to exploit these efficient architectures in the best way possible and provide sort of a rich set of operators and capabilities to domain experts. And then at the very top of all this is systems where people are building models that need to be structured that map and exploit this hardware and software in the most efficient way possible. So we have techniques like quantization and pruning and neural architecture search, as well as other novel data science applications. And so really it's through all of these 3 things that we achieve the most efficient possible systems for machine learning. And so with that, I will introduce our keynote speaker, Sam Davis. Sam Davis is the head of machine learning at Myrtle.ai, where he works to understand and develop efficient state-of-the-art machine learning models. His interests and work focus on the intersection of conversational AI, model compression, and hardware design for machine learning inference. He chaired the MLPerf working group to develop the speech recognition benchmark that was released as part of the recent 0.7 inference round. So with that, please give a warm virtual welcome to Sam Davis.
Great, thanks, Michael. I'm just going to take a second to share my screen. Okay, could somebody confirm that you could see that okay?
Yep, looks good.
Great, thanks. Well, yeah, it's really great to be here today on what is a cold evening here in the UK. And I'm excited to be here as well, as this workshop, as well as the challenge, are really a key part in driving the adoption of AI and tackling the practical issues that this brings. And there's also a really great lineup of speakers that I'm excited to listen to as well. Myrtle.ai itself, we're a UK-based company that optimizes machine learning inference workloads for multiple applications in both cloud and enterprise data centers, as well as in edge applications. And we have a product called Seal that can improve the compute density of recommendation systems by up to 10 times. And these models are the ones powering search, advertising, and other personalized content. And we've recently released a solution with Intel that they announced during Supercomputing 2020 last month. And that's the work I'm here to talk about today. And we're going to do a deep dive into some of the parts of. But before starting that, I really want to give some context behind the work that we announced. And for some time now, there's been an exponential growth in the capability and pervasiveness of artificial intelligence, machine learning, and in particular, deep learning. And I'm sure many of you have seen the graphs presented by OpenAI and others such as Intel that show the nice exponential growth curves for deep learning model sizes and compute requirements. But ultimately, the result of these exponential curves is an ever-increasing use of machine learning, deep learning inside a wide range of products and services. And this includes both products and services that already exist, as well as new ones that we haven't thought of yet, or had the capability to do previously. And a great example of using AI in improving existing services that everybody uses every day is the use of BERT in improving search. So BERT is a transformer-based neural network published in 2018, but it now powers nearly all queries behind two of the world's largest search engines, Google and Bing, as they first described in these blog posts. And more recently, over the last few years, advances have enabled people to deliver new interfaces for users to interact with the technology, such as through the increasing use of voice via personal assistants like Amazon's Alexa, Apple's Siri, Google Assistant, and Microsoft's Cortana. And these now provide the main interface for many people to control their home, play music, find the answer to a question, and much, much more. And this particular area that includes voice interaction is part of conversational AI. And conversational AI is one such area where rapid growth and advancements are playing out today. Now, the exponential curves that we previously spoke about are being driven in improvements in three key areas, which nicely aligns with Michael's introduction, but with a slight difference in terminology, I suppose. So whilst algorithmic and software advances have been significant, hardware improvements have been the consistent driving force for the continued improvement in AI. And one of my favorite quotes about this is from an article by Rich Sutton, one of the key figures in reinforcement learning. He states that the biggest lesson that can be read from 70 years of AI research in general is that methods that leverage computation are ultimately the most effective and by a large margin. The ultimate reason for this is Moore's law, or rather its generalization of continued exponentially falling cost per unit of computation. However, with the slowing or ending of Dennard scaling and Moore's law, we've known for a while now that we will need to work harder to keep these exponential growth curves going. And to achieve this, we need to take a more holistic approach and advance all of these three pillars, in my case, algorithms, hardware, and software, together. However, any individual one of these areas is challenging and not solvable by a single person or a single team, which means that inter and intra-team, departmental, company, and industry collaborations become increasingly important to the long-term success and advancement of AI. And this talk is going to focus on a conversational AI application, in particular speech synthesis, that has seen a wide range of applications and deployment inside of data centers because of this. Because of its pervasiveness, speech synthesis has a vast throughput requirement, and we're not just limited for resources at the device level, but also at the data center level, as we can't simply build more data centers to meet demand. So again, we need to take a holistic approach to creating an optimized solution. And the solution we're presenting today combines each of these three components, as well as a successful collaboration between two companies to deliver this step change in performance. The collaboration was between us at Myrtle.ai and Intel's Programmable Solutions Group, or PSG. The algorithm is a real-time state-of-the-art neural speech synthesis model known as WaveNet that was developed by DeepMind. And we also look at a new quantization format called block floating point 16, or Microsoft floating point, which is a variant of block floating point. And the hardware was Intel's new Stratix 10 NX FPGA that has AI tensor blocks and HBM2 memory. Both the AI tensor blocks and the HBM are themselves reasonably recent advancements that are now seeing widespread adoption. And the software that brings us all together is Myrtle.ai's MAU Accelerator technology. So this talk is going to introduce conversational AI, and then we're going to look at our speech synthesis solution to see how it combines advancements in each of those three areas to achieve the step change in performance. And to do this, we're going to look at the algorithm side, and we're going to see that the individual parts involved in typical neural speech synthesis applications. And we're going to do a deep dive into the WaveNet architecture to gain an understanding of why it's a challenging model to deploy. We're then going to look at the hardware, where we'll discuss the challenge of deploying WaveNet using existing hardware and programming paradigms, despite having relatively few parameters and operations per inference. And we'll also look at their new AI-optimized FPGA and the novel quantization format that it supports. And finally, we'll look at the software component and the importance of programming model and accessibility, as well as the quality implications when using lower precision number formats. And we'll finish by bringing all of these components together to compare the WaveNet performance versus other implementations. So we're going to start by looking at conversational AI, and the speech synthesis solution that we're going to look at today is part of this application space. But what actually is it? Well, conversational AI allows the natural interaction between you and the devices you use. And this is the user's view on conversational AI. So they speak into a device and it forms and articulates a response. However, there's actually a lot going inside this component that includes network interaction, as well as processing at both the edge and in the cloud. And for our discussion today, the three main components of this internal view are going to be processing the user's speech into some representation such as text, extracting the semantic information and using this to formulate a response, and synthesizing this response into an audible version. As we saw earlier, there's a large-scale use case centered around voice assistants, with personal assistants now present on nearly every mobile device, as well as in devices such as Google's smart speakers and Amazon's Echo line of products. The non-obvious applications for you that can use all or part of this pipeline also exist and include call center automation or call center worker assistance, personalized call screening, and automated booking systems like Google's Duplex. One thing to note about conversational AI is that it's a rapidly growing application space in terms of users, use cases, market size, and technology, and it also presents a number of interesting deployment challenges. So some of these challenges include the users themselves. If the product is successful, it often sees widespread usage, leading to a large volume of application requests. And it may be an internal product that is then used by external-facing teams, or it might be an external-facing product itself. Each of these application requests requires coordinating a pipeline of machine learning models. And each of these models itself has a large throughput requirement. So the challenge here isn't necessarily about users, but the throughput at scale that they bring. The second challenge is quality. Users only continue to use a conversational AI service if they have a positive experience. And even one negative experience can have an impact on the user's view of a conversational AI product. And therefore, the model quality needs to be consistently high. And this has implications on the model, as it often means they change rapidly and are pushed to being ever larger and more complex. And one of the third challenges is latency. So conversational AI applications are typically interactive, meaning that the time they have for the application to produce a response is less than a few hundred milliseconds. And as the product contains a pipeline of models, the tail latencies of each model compounds. So it's critical that each model has an extremely low tail latency to combat this. And here, tail latency is defined to be the latency at which some percentile of the queries have completed by. For example, this percentile is typically something like 99% or 99% of all queries being answered within that latency bound. And this challenge pushes the models in the opposite direction to the quality tail. We want them to be smaller, less complex, and change less frequently. The good news is that we can often do this via model compression and distillation and similar techniques. So we can see how both throughput and latency strive to drive model size and complexity down, but the quality demands strive to drive model size and complexity up. And finding the balance is a challenge, but continued advances in the three pillars, algorithms, hardware, and software, allow you to improve all of these factors simultaneously. So I'm now going to briefly move on to show our solution demo. And what it does is exactly this. It produces high quality, high throughput, and deterministically low tail latency speech synthesis using hardware, software, and algorithmic advances. And we're going to go into each of these components in detail. But first, we're going to start with a demo. I hope this is going to work. So this demo contains a web interface that I'm going to actually link out to at the end of my talk, so you can play with it and type in some of your own text. I'm going to start by playing this video, and you'll see it type in the text on the left, and then click Speak It. The audio will start generating, and then it'll play once it's finished generating the entire sequence. Okay, great. So we're going to start by looking at, let's play again. There we go. We're going to start by looking at the algorithm component, which is mainly neural speech synthesis. So the typical neural speech synthesis pipeline receives text as input and produces an audio file containing the synthesized speech corresponding to the text as output. And whilst there are models beginning to appear in the literature that go directly from text to audio, the more common approach today is to break this problem down into two easier parts to solve. The first part is a model or number of models that produce features from the text. And the one we're going to use in the demo is called Tachytron 2, that produces a spectrogram representation of the audio shown in the middle here. The second part then takes these features and produces the audio output. And the focus of today's talk is going to be on this, and in particular, the model known as WaveNet. And WaveNet is extremely challenging for existing and hardware software and software during inference. The PyTorch implementation we actually use for training the model takes minutes to generate seconds of audio at inference time. And whilst there has been research in producing models that are more suitable for existing hardware and software, they typically reduce quality or add significant complexity, either during training, inference, or both. So beginning to look at the WaveNet model itself, WaveNet is a generative model that aims to output the next audio sample given all previous ones. And this is shown by the diagram on the right here. That is a zoomed in section of an audio clip where the Y dimension is time and the X dimension is sort of audio sample quantization level. The WaveNet model is trying to predict a probability distribution for the orange circle on the right given all of the blue ones. And this can be written as the following distribution P, where the concrete values are denoted y sub t in orange, and all previous samples here are given by the blue y sub less than t. And we also have an additional feature variable f, but with conditioning on. And these are the features that are going to allow us to control what the model outputs. And for our use case of speech synthesis, it will be features derived from the text. More concretely, for 16-bit audio, the possible output values represented as the orange y here are between 0 and 2 to the power of 16 minus 1. And the possible input samples are also within this range. And these values are typically represented via a one-hot encoding. And the features that we condition on can vary, but we'll use the spectrogram representation as mentioned earlier. So stepping into the next level of detail, we see that WaveNet can be thought of as a causal 1D convolution over a window of previous samples and features. And the convolution is causal because it only receives input from a window of previous audio samples and features, with the features controlling the generation. And here, the resulting window size is 8. Training this model is reasonably straightforward. The input is an audio clip or a segment of an audio clip, and the features are features derived from this audio clip, such as the spectrogram. The target outputs can be the same audio clip as used for the input, but shifted right by a step. And this means that the forward and backward pass through the model can be run entirely in parallel at all possible positions in time, making the effective batch size in the thousands or tens of thousands, as audio sample rates are typically 16 kilohertz or more. And such a large batch size makes it highly suitable for training on GPUs and GPUs. And we can then minimize the negative log likelihood using gradient descent. So we've seen that training WaveNet follows an approach similar to most models, but this changes during inference or generation. Now the model needs to generate each sample sequentially. For example, here we see that the model is so far output 10 samples at the bottom, and it's generating sample number 11 in orange at the top here. Once it's generated sample number 11, it then uses this as the 11th input and can proceed to generating sample number 12. And note that we actually have all the features up front, as these are produced by a model such as Tachytron 2. This process then continues, so the model outputs sample I, and this is used as the next input step. And each time step must be generated sequentially, so the batch size is reduced significantly. And to generate audio in real time, we must be able to do this at 16,000 steps within a second for 16 kilohertz audio. And this requires essentially doing a complete forward pass through the model, as well as sampling from the probability distribution P to get a concrete Y, once every 62.5 microseconds. So now we know how WaveNet works, we can look at more detail about the architecture itself. We've seen that it models the probability distribution given here, and that it takes a window of previous samples to produce the next one during inference. We said that this can be viewed as a causal convolution and drew this blue triangle that could be slid along the input. Looking at it in more detail, we see that to produce the ith sample, here in orange, given a previous number of inputs, the model first embeds the one-hot encoded values to form the light green nodes. These are combined with the features derived from the text, and a causal convolution is applied to create the next set of hidden nodes. This is repeated a number of times, and the dilation size of the convolution increases. This has the impact of exponentially increasing the window size of the input that the model is able to see, whilst keeping the total amount of computation constant. And finally, the output produced in here shown in red is produced. This is then put through some final layers to produce the output distribution P, here in orange. Now note that to produce the ith output value, again in orange, we only actually need to compute the rightmost column of hidden nodes, because all of the previous hidden nodes have been computed during past time steps, and hence we store their values and retrieve them when required. Not all of the hidden states here on the left are actually still required, but I'm going to leave them there just to simplify the diagram. But the key thing is that we must actually store and retrieve from a window of activations for each hidden layer. So now we're going to briefly look at this visual description in a written form. The model starts by embedding the one-hot encoded inputs to produce a set of hidden nodes. And these, along with the features, are input to a gated activation unit to produce a hidden state Z that is not represented in the previous visual form. This value is then fed to another linear layer, which is added to the previous hidden value via a residual connection to form the new hidden state. And this process, or residual block, repeats for the desired number of hidden layers, which is typically somewhere between 20 and 40. The gated activation unit itself is where the dilated causal convolution occurs, and it has two paths. The first applies a convolution to the hidden states before adding the features and applying the tanh activations function. And the second also applies a convolution to the hidden states and adds the features, but applies the sigmoid activation function. And these are then element-wise multiplied to form the output. And this form is similar to the gating mechanism inside a GRU or LSTM for those familiar with those sort of architectures. Coming back, we see that the red output O is actually a sum of all of the intermediate Z values after a different linear layer has been applied to each. And this effectively enables the model to model different audio frequencies. And finally, this output O is put through a small MLP before the softmax function is applied to produce the output distribution. So pausing here, we see that there are a large number of operations in terms of not computation, but actual calls per forward pass. And the naive implementation on an existing architecture is therefore generally bad given the latency constraint. As if done naively, each of these operations has to be launched, scheduled, read from memory, and write to memory, all within the latency bound. So summarizing the key, or some of the key characteristics that we've talked about in the past few slides, the model is autoregressive and generation occurs sequentially. And to generate audio in real time, this must happen thousands or tens of thousands of times a second, meaning that a single forward pass through the model has an extremely small amount of time to complete. And the model has a residual backbone that consists of causal dilated convolutions, and that during inference, each of these must read previous activation values and store new ones. So that's a walkthrough of the WaveNet architecture that we're using for speech synthesis. So now we know the architecture. From a purely algorithmic perspective, our aim is to maximize some form of quality metric. And for speech synthesis, this is typically mean opinion score, or MOS or MOS, but there are other variants used. And mean opinion score asks people to answer the following question for a given piece of audio. How natural or human sounding is this recording? And it then asks them to respond using the following scale that has ratings from 1 to 5. It takes the responses from a number of users over a number of samples and averages them to produce a mean that has a value between 1 and 5. And although this metric is commonly used, direct comparisons in the text-to-speech literature is often difficult or impossible because people use different data sets or different test set splits, and the exact evaluation technique for MOS can differ as well. For example, in some instances, users are subjected to a listening test prior to being allowed to answer, or they can have varying English ability or being used to different accents. And the results often have confounding effects as people change more than one thing to sort of hack the results. And an easy example of this is to produce higher frequency audio samples than other paper, which lead to unfair comparisons. But despite all of this, WaveNet is still considered the state of the art and the model that is compared against, despite the original paper from DeepMind being released in 2016. So for the WaveNet architecture that we talked about, what are the dials we can tune to improve this quality metric? Well, the most common ones are number of layers or model depth, and a deeper model typically improves quality. Number of layers, larger hidden sizes, number of layer dimensions, sorry. Larger hidden sizes typically improve audio quality. And audio frequency is higher sampling rates, as I said before, are typically rated higher by users. But there are lots more. But the main thing is with each of these, they do not come for free. And they nearly always increase the compute requirements of the model and therefore decrease the throughput and increase latency. And this brings us back to the original discussion around the 3 pillars of hardware, algorithms, and software, because we cannot optimize any one of these individual components alone. And this brings us nicely to the hardware component now that we've seen the compute characteristics and requirements of the algorithm. So from a purely hardware perspective, the aim is to maximize some form of performance metric. And for this use case, and many others, is latency-bounded throughput. And in practice, we're recording these metrics at 2 different levels. At the application level, this aims to maximize the throughput for a given latency SLA for the entire end-to-end conversational AI pipeline. But the level we're going to focus on today is the model level, where the aim is to maximize the latency-bounded throughput for a given model. And in this case, we're looking at WaveNet. So we can actually plot Pareto frontiers for various different WaveNet configurations that are based on the quality dials that we previously talked about. For example, here are the 3 different hypothetical models. And as we increase throughput, we typically see latency increase. But in practice, the curves might not be as smooth as this. So now we have these curves, we can look at the hard latency bounds for a forward pass based on the audio sample rate that we wish to target. So for 16 kilohertz audio, this is 62.5 microseconds, here shown in the green line. And then for 22 kilohertz audio and 32 kilohertz audio, these are given by the orange and red lines. So given this plot, we could then work out which model we want to select based on the quality and performance metrics. But again, in practice, we likely don't have these curves or full set of quality results. And the Pareto curves themselves do depend on the implementation and platform that you're using. So we've said that we're running WaveNet for inference on it, and we've looked at why this is, or we've said that this is not ideal on existing accelerators. But why is this? Well, if we log a single call to a residual layer, which implements these equations that we looked at previously, we can see that current programming models of existing accelerators typically launch a kernel per operation, where each kernel is denoted by one of these boxes shown in the middle of the screen. So this pass alone for a single call to the residual block took 74 microseconds, which is way above the budget that we have to generate 16 kilohertz audio in real time, where it was set to 62.5 microseconds. But there will be some profiling overhead in this call, but we're way over the budget just for this one layer. And it's common to have tens of these residual blocks. And there are a number of other operations both before and after the residual layers as well. So it is possible to actually handwrite a kernel that is able to meet the latency bound by fusing all of the operations into a single kernel and then launching this once. However, this approach, or sort of using persistent kernels, breaks the typical programming models and can be fiddly and error-prone to implement and deploy. So the type of models such as WaveNet are therefore well suited to a platform and programming model that doesn't have the overhead of scheduling and has known latency bounds per call. And Intel's new Stratix 10 NX FPGA is an excellent example of a platform that provides exactly this. Its FPGA architecture facilitates the flexibility to service rapidly changing model architectures, which are especially prominent in areas such as conversational AI. And we introduced BERT at the start and how that's changed the search landscape despite only being published in 2018. And later on, I'll talk about how this flexibility has allowed us to efficiently sample from the output distribution P. It contains up to 16 gigabytes of HBM2 that provides the large memory bandwidth required for many neural networks. And it also contains AI tensor blocks that provide the large compute bandwidth requirements for neural networks. And we're going to look at how we've exploited each of these components in the WaveNet implementation that we use in our speech synthesis solution. So we're going to start by looking at how we've used the FPGA's architecture to achieve efficient sampling of the distribution P. So recall that the model produces the output distribution by applying some layers to the red O before computing a softmax distribution. And it then has to sample from this distribution P to get a concrete value Y sub t that can be fed as the next input. And here we've added new temporary L, as it's going to make it easier to talk about some of the parts later. The softmax function itself, as well as the sampling, is expensive in terms of logic and time. For example, a naive implementation of n values requires at least n applications of the exponential function, n-1 additions and n divisions for the softmax function, and order n additions and comparisons when sampling. Now, while the FPGA architecture and fabric provides flexibility in terms of compute and memory resources, they are still limited, and softmax and sampling are therefore prohibitive. But given this, the first obvious question to ask is whether we can actually get away with just choosing the mode of the distribution P at each step. This is cheap to do because it corresponds to picking the largest value before the softmax operation, and therefore we can set Y sub t to the argmax of L. However, it turns out that the audio quality produced by this is poor. And to demonstrate this, I have two samples here in the bottom right. The first one is synthesized audio using Tachytron 2 and WaveNet with softmax plus sampling. And the second one is where the audio has been synthesized using Tachytron 2 and WaveNet, but with argmax over the values in L. So I'm now going to play them both in turn. So that was the first one, and the next one is done using argmax. I'll just play them once more so you can compare. So we can see the audio quality of the argmax sample is actually quite poor. It's squeaky and there's lots of clicks and noises. But why actually is this? Well, it's related to the under-discussed area of typicality in generative models. And in particular, at a high level, the majority of the probability mass of the high-dimensional distribution is not actually near the mode, and therefore the mode is not representative. And a good example for this is a high-dimensional Gaussian. So if we create a 100-dimensional Gaussian with mean 0 and identity covariance, and then draw a lot of samples from it, and then record the Euclidean distance from the mean of each of these samples, we can plot the distribution of the distance of the Euclidean mean from 0. Distance of each sample, Euclidean distance of each sample from 0. And we can see that in this sort of very small plot here that they cluster around 10. So this goes against our intuitions when we think about most of the probability mass of a Gaussian distribution being centered around 0. And a similar effect is actually happening for our distribution P. So therefore, we've seen that we must sample, but how can we do this efficiently without actually using a lot of resources? And it turns out there's a very neat way of doing this called the Gumbel max trick. And that sampling from the distribution P is actually equivalent to taking the argmax over L, but with a new vector of values G added, as long as these values G are drawn from a Gumbel distribution. And I'm not going to go into the details of this today, but we at Myrtle.ai have some IP to implement this efficiently using the flexibility of the FPGA fabric, meaning we get high quality audio with minimal resource utilization. The Stratix 10 NX FPGA also has HBM2 memory. So as we discussed earlier, at each step during inference, we must read previous activations and write new ones. And we actually use the HBM for this, as it provides large read and write memory bandwidth for this cached set of activations. Intel's Stratix 10 NX FPGA also contains AI tensor blocks, which provide comparable compute bandwidth to other ASICs and accelerators. And these are tuned for common matrix-matrix or vector matrix multiplication. And there are 3,960 of the AI tensor blocks on the device. And each AI tensor block has 3 columns, or in the diagram on the right here of the slides, 3 rows that are capable of performing a dot product. And at 600 megahertz, this equates to 143 int8 tops, or 286 int4 tops. And the interesting thing is that the AI tensor blocks also support block floating point 16 and block floating point 12 with int32 or FP32 accumulation. Now, block floating point is a reasonably old number format that has been around for a while, but today it is not seeing common use in deep learning. So we know that neural networks are able to cope with reduced precision, even down to single bit during inference. However, single precision floating point, or FP32, is typically the most common format that people start training in inference with. It has a single sign bit, an 8-bit exponent, and a 23-bit mantissa. And more recently, platforms have begun to adopt bfloat16, or brain floating point, as it provides the range of FP32, whilst maintaining enough precision to train neural networks, and it also avoids the requirement of dynamic scaling that's required when using half precision or mixed precision during training. And it does this by maintaining the same number of exponent bits as FP32, but by truncating the number of mantissa bits to 7. For inference, people typically go one step further and use 8-bit integers, or int8. This results in significant speedups with little to no loss in accuracy, but often requires calibrating models after training. It may even include quantization-aware training that simulates the noise introduced by quantization during the training process in order to improve the accuracy during inference. Now, block floating point aims to maintain the range advantages and ease of use of FP32 bfloat16, whilst providing the power, performance, and area advantages of int8. And it does this by having one shared exponent for a block of numbers. And in this example, we have 5 numbers that all share the same exponent. All calculations can then be done using fixed point hardware, and the exponent itself is chosen to be the largest exponent in this block of values. So the trade-off with this format is that all values in the block should be similar orders of magnitude, else those with lower magnitude end up losing precision. And all of this, using a block size of, say, in this case 16, results in a 2 times memory saving and a 2.8 times higher arithmetic density compared to bfloat16. And on the slides here, you'll note that it also says Microsoft floating point, because Microsoft recently released a paper during Europe's this week that goes into detail about this floating point format and how they use it. For the WaveNet implementation, we take a block size of 10, or bounding block size of 10 over the channel and activation dimensions to match the size of the AI tensor blocks. So we now come to the software component that completes these 3 key pillars that we've been talking about. And in this case, we're going to focus on Myrtle.ai's MAU accelerator technologies and proven design techniques. So the WaveNet model that we've been talking about has a relatively low number of parameters and compute operations per second compared to other neural networks that are commonly used. Highlighted in blue here are the values for the specific configuration of WaveNet that we've used in our speech synthesis solution. So we can see in the first column that the model itself only has 2 million parameters in total, and therefore the total number of operations per second to generate 1 second of audio is 65 gigaops. So these values are orders of magnitude smaller than other neural networks models, as well as other models that are used for speech synthesis. But it's also worth noting that this table leaves out the parameters and operations for layers that modify or upsample the features, as they aren't strictly part of the autoregressive wavelet loop that we've been focusing on so far. But despite these low totals, WaveNet performs poorly on CPUs and GPUs due to the latency requirements, complex control flow, and programming model. And as I mentioned at the start, the training implementation actually takes minutes to produce seconds of audio on a GPU. And that we've also seen that FPGAs are a great alternative platform for scenarios such as this one, especially if there are other constraints, such as the use of non-standard operations or the desire to use quantization formats that aren't supported on other platforms. However, accessing the capability of FPGAs and non-standard numerical formats and precisions for deep learning models has typically been limited by the tooling, especially for models that are anything but ResNet 50 using FP32 or Int8. For example, if we look at the recent MLPerf Inference v0.7 results, we see one entry from Xilinx and Mipsology in the data center category for available systems. And this is not just due to a lack of performance, as we at Myrtle.ai have demonstrated through several engagements that it's possible to gain factors of 10 in performance for workloads over other accelerator platforms, even when using standard performance comparisons that don't normalize by the number of flops on the board. But rather, it is instead limited by the platform and ecosystem abstractions that are available for ML users. And using what is there today requires an understanding of the complete stack from machine learning model down to FPGA platform. And this requires a wide and deep set of skills. And in order for the FPGA to see widespread use, we must therefore be able to decouple this skill set requirement. And one such way of doing this is through one of the key points mentioned at the start of the talk. And this is through collaborations and partnerships. So for example, collaborations between internal teams or partnerships and engagements between companies. And another way is to improve the platform, ecosystem, and tooling to provide the right level of abstractions to users at all levels. And Myrtle.ai's MAO accelerator technologies and experience enables exactly this. So our technologies and IP are an enabler for the use of the FPGA platforms, including Intel's recent Stratix 10 NX FPGA. And the extractions they can provide mean that we can bring together people with different skill sets across the complete stack, and that we can also engage with partners to achieve 10 times latency-bounded throughput on a wide range of workloads. So some of the key parts of this technology that we'll discuss today that are relevant to the speech synthesis solution are the configurable MAO architecture overlay and the ability to support a wide range of quantization formats and improve the accuracy of them, if necessary, through quantization-aware training in existing deep learning frameworks. Our MAO accelerator extraction consists of the overlay architecture that contains a number of MAO cores, and the exact number of cores can be configured depending on the target platform, enabling our technology to scale up and down. The MAO cores themselves can be easily reconfigured for specific applications and required functionality, and make optimal use of available resources whilst reducing the complexity of programming the device. And they are also able to include other features, such as our patented unstructured sparsity acceleration. And this extraction has two effects. It reduces the complexity of programming the device, which is one of the major challenges in it bringing acceleration to the market. It also provides ML engineers and users an extraction for them to target. And in the diagram on the right, we have the actual design of the MAO cores used in our speech synthesis solution. In that there's 4 of them, with each having this sort of layout. And there's a larger image of this, so you can see the exact details found in the white paper that I'll link to at the end of the presentation. And the second component of our technologies that is relevant to this solution is the ability to support software simulation of non-standard quantization formats, including block floating point. So we've seen that whilst neural networks are resilient to loss in precision during inference, lower precision formats can result in quality degradation and can be greater than 1% when using 8-bit integers if conversion is done after the training process has ended. Now, the block floating point format that we introduced earlier is actually quite resilient to this already due to the ability to keep the range. But if we recall the final part of the network that took the value O and applied an MLP before applying the softmax operation, here I've actually given the 2 linear layers subscripts or indexes. So the first one is linear 1 and the second one is linear 2. And if we evaluate the quality or MOS of this model using FP32 for both the linear layers, this gives us around a MOS score of around 3.9. If we then naively convert both of these linear layers to the block floating point 16 format, in this case, I'm going to denote it Microsoft floating point for reasons we'll see in a minute, we see that the quality drops a bit to 3.7. And if we use our simulation tools to do quantization-aware training, we can actually recover some of this accuracy degradation, going up to 3.8 in this case. So quantization-aware training works by simulating the quantization noise during training or fine-tuning. And it does this by converting the parameters and activations to the same range and precision of the target type during inference for the forward pass, and then uses a straight-through estimator for that pass on the backwards pass. And this results in improved model quality as the model learns to cope with the added noise. But as quantization-aware training requires changing the training code or doing additional epochs or iterations, it's interesting to see whether we can avoid this. And for Microsoft Floating Point, the answer is yes. All that needs to be done in this case is to keep the final linear layer, here linear 2, in higher precision. And for the example in the table, we're using FP32, and we see that the accuracy has recovered to be within the same confidence interval as the full FP32 version. And it's actually even possible to use lower precision formats such as bfloat to see the same effect. And Microsoft's recent paper in Europe's presents a table of results for this approach, where for the conv models or CNNs, the last layer is actually kept FP32 and the rest is converted to Microsoft Floating Point 16 or Block Floating Point 16. So we can see that for nearly all of a wide range of models in this table, the quality of converting to Microsoft Floating Point 16 from FP32 after training has completed remains the same. And this includes a lot of models, including ResNet, InceptionNet, EfficientNet, as well as some of the RNNs that Microsoft uses in production, as well as different applications of BERT, as we see at the bottom there in the transformers row. So I should say that the column on the right here is accuracy relative to the FP32 format. So MobileNet V1 is the only one that differs, and even then it's 99.8%. The accuracy is 99.8% of the FP32 version. So to summarize the software component that we've discussed, we've seen how this is the limiting factor for the adoption of FPGAs for machine learning and deep learning today, and how advances in the ecosystem, as well as collaboration, can be used to solve this. And Myrtle.ai's MAO accelerator technologies and experience, extractions that enables the stack to split at multiple points, and that this and our IP is an enabler for us to partner and engage with people to achieve 10 times acceleration for specific workloads. So now we're going to step back again and look at the bigger picture, and then summarize how we've combined these components to deliver the speech synthesis solution at scale. So we've discussed how conversational AI and voice interaction is a rapidly growing application space in terms of users, use cases, market size, and technology, and it also presents a number of interesting deployment challenges. And we know that ML is powered by advances in hardware, software, and algorithms, but the ability to rely on hardware is slowing, and therefore we need to take a holistic approach to advancing all three together. For each of these three areas we've walked through, some of the techniques that we've done to achieve our end speech synthesis solution include algorithmic advances that have led to models that can produce near human quality speech synthesis. And we've seen that these models are challenging for existing hardware platforms and programming models. Hardware advances provided us a powerful and flexible compute platform that are well suited to the rapidly changing AI landscape. But these can be difficult to access due to the ecosystem. And we've seen that software advancements are vital in enabling users to bridge the gap between the algorithmic and hardware advances and utilize new programming paradigms. And they also enable inter and intra-team and company collaborations and partnerships. The result of bringing these all together is a step change in performance for the conversational AI application, which is speech synthesis. So shown on the left here is our demo user interface that Intel presented at Supercomputing 2020 this year. And on the right, we have the various performance comparisons against NVIDIA's handwritten CUDA implementation running on a V100 for varying audio sample rates. We see that for 16 kilohertz, our solution delivers an 8 times higher throughput. At 24 kilohertz, this rises to 10 times. And at 32 kilohertz, an audio sampling rate of 32 kilohertz, the last row in the table, our solution achieves a 16 times higher throughput. This is a step change in performance, and it's key when optimizing not just device power performance and area, but also data center power performance and area. So if you want to find out more about this solution, there's a lot of content available. We have a blog post with Intel where they detail our solution, a joint white paper that goes into the technical details and includes the diagrams about the overlay architecture as well as the null cores. And we also have a video about the solution that shows the speech synthesis quality. And there's also a link to the interactive demo that I showed at the start of the talk, if you're interested in trying out some of your own text and seeing the results. I'll post these slides somewhere. I guess the conference organizers will let me know where I can do that. And you'll be able to click this link and generate your own audio. And finally, if you're interested in deploying our solution or have a need for optimizing any of the machine learning inference workloads across any platform, please feel free to get in touch with us either via these links or reach out to us via our website. Thanks.
All right, yeah, thank you, Sam. We have a couple of minutes till our next talk, so if there are any questions that folks have, we can do that now. I think folks are muted on Teams, so if you have a question, you can unmute yourself.
Just so you know, there is a hand sign button, so if you want to ask question, press that and then we can unmute. Either way it works.
Satya was asking a question. I have a question. So what do you think, so it seems like these models are still pretty large. So you're running them, and I think you mentioned like the FPGA that you're running had something like 16 gigabytes of RAM.
Mm-hmm.
What do you think it would take to sort of scale down and compress these kinds of models to run on the edge directly?
Mm-hmm. Yeah, it's a good question. So the HBM we don't actually use all of. We just use it mainly for caching that sort of small sliding window of activations during the WaveNet operation. So all of the parameters themselves are already stored in on-chip memory, which is, I guess, good for more on-device use cases. And Microsoft's floating point format also enables to go even lower. So they have sort of a Microsoft floating point 12-bit version, which has a slightly smaller mantissa. But in most cases, you do actually end up needing to use quantization-aware training again. And sort of the third wave compression that we've explored is sparsity. So we've actually not explored or looked at sparsity in this presentation, but we have some work and some publication on arXiv that looks at compressing the WaveNet model via sparsity. And we achieve sort of 50% all the way up to 75 and 90% sparsity results, and the quality degradation that they achieve sort of gradually, the degradation gradually goes up, so they get lower quality as you get to sort of the higher compression ratios.
And how, so, when I guess you mentioned, that like the evaluation metric is, kind of I guess it's sort of a challenge because everyone has like a different metric, and the metric is sort of, it seems like a little bit of a, it's sort of a non-precise metric, sort of saying, oh, well, I think this sounds, very natural or unnatural. Can you comment on like how, I think folks like MLPerf are kind of handling, those kinds of evaluations? Like, is that something people try to consider when they make these performance comparisons?
Yeah, so yeah, MOS score is definitely a difficult one because it is subjective, as you say. And for things like model compression challenges, I guess, such as this one, as well as MLPerf, which is, I guess, a proxy for compression through performance, it is one of the difficult things to look at. And so far, I think MLPerf has avoided speech synthesis for that reason, because doing subjective comparisons is a difficult thing. And I think the other component is that model quality is also not a linear scale, typically for subjective metrics like this. So when I was talking about the difference between a MOS score of 3.7 and 3.9 earlier, in practice, you probably wouldn't actually notice a difference, despite it being like a quite a significant absolute accuracy drop compared to other tasks such as image recognition or object detection.
Thank you. Are there any more questions for Sam before we switch over?
Hey, Sam, earlier you made a comment about platforms with lower scheduling needs being more suitable for these kind of applications. Are there other such platforms other than FPGA?
Yeah, there's definitely a wide range of accelerators coming out now, and there's probably around 100 different accelerators coming out, and I'm sure that there is a subset of them that use the similar programming model where they schedule ahead of time rather than doing it in the hardware itself.
Got it. Thanks.
Yeah. Okay. Yeah. Thank you, Sam. That was a great keynote talk. I think a great way to start EMC2. And so we appreciate your attending today.